Okay. Okay, so now we will talk about matrix powers. Okay, when we talk about real numbers, as you know, that's we have some operations like addition, subtraction, blah blah blah. Right? When we just add a number to itself a few times, for example, let's say, let me use green, dark blue. If we have, for example, real number a plus a plus a in compact form, we can just write it as 3 times a, right? And how about if the number itself is multiplied by itself, let's say a times a times a. Actually, every time writing in this way, it is not a practical way. That's why actually mathematicians, they introduce another notation that is exponents. So we can just write it as a to the power 3. That means that a number is multiplied by itself 3 times. In a similar way, we can introduce this power for matrices. For example, here, a to the power k. How is it defined here? That means that this A, matrix A, is multiplied by itself k times, right? So that means that if you are given matrix A, let's say A squared, that means that A times A. Well, it's not dot product, just matrix product. For example, A cubed, that is A times A times A. This is how we introduce power for matrices. And here we also define that a to the power of 0 is equal to IN. What does IN? It is an identity matrix, right? That means that all the entries in the main diagonal, they are ones, right? And here we have other entries, they are zeros. All here we have zeros, okay? And here we have IN, means this one is n by n matrix. A to the power 0. And also real number, we know that any number that is not equal to 0, a to the power 0, actually is equal to 1, right? Why is this so? Because why we are defining like this? Because a to the power 0, we can just write it as a to the power n minus n. Or that is just a to the power n times a to the power minus n. And later we will just actually, what is it, define this as the inverse of this matrix. I can just write it as a to the power n to the power of negative 1. Anyway, if A is a square matrix and R and S are non-negative integers, then A to the power R times A to the power of S, that's equal to A to the power of R plus S. It's very similar to real number. We just add their exponents or powers. And how about a to the power of r to the power of s? That's just equal to a to the power of r times s, r times s. And by definition, we can prove this. It's very easy, but just I'll skip the proving part. Consider the following matrix, for example, A times B, right? Okay. Let's start with the first one. A, matrix A, that is 1, 1, 1, 1. All right. And let's just consider these powers. For example, A squared. What is A squared? That means it is A times A. So by the definition, we can actually write it as 1, 1, 1, 1. So we should multiply this matrix by itself, 1, 1, 1, 1. So if you multiply this, what we have here, 1 times 1 plus 1 times 1, that's equal to 2, 1, 1, 1, 1. So also this is 2, and also this is 2, this is 2, right? And I can just write it as 2 because 2 is a common factor of all the entries here. Just write it as 2 times 1, 1, 1, 1. Just scalar multiplication of this matrix, right? And how about A cubed? A cube, I can just write it as A squared, let's say times A by the definition, right? It's because R3, I can just write it as 2 plus 1. Here we have A to the power of 2, A to the power of 1. What is A squared? We have just calculated here. That's equal to 2 times, here we have 1, 1, 1, 1. And here we have matrix A, that is 1, 1, 1, 1. And this one is A squared. We have just already multiplied here. So that's equal to, what is it? 2 times 2 times the original matrix. and which is equal to 2 squared, and here we have 1, 1, 1, 1. Now, if I just continue here, as you see, we'll have a pattern, right? When it is 2, here we have just 2, and the matrix itself, I can just write it as 2 times A. And how about here? Here we have 2 squared times A. And how about A to the power of 4? I can just write it as A cubed times A, right? Or A times A cubed, doesn't matter. And what is A cubed? A cubed equals this. That is 2 squared times A times A. Because A cubed equals 2 squared times A, and here we have A. That's equal to 2 squared, A squared. And what is A squared from here? That's equal to 2A. So that is 2 squared times 2 times A. That is 2 cubed A. So as I say here, now we see a pattern. Here we have just 2 times A, and here we have 2 squared A and 2 cubed A. The difference between this power of matrix A and the power of 2, only 1, right? If it is 4, that's equal to 1. If it is 3, that's equal to 2. So now we can just conclude that then if we just multiply this, A by itself n times, then here we will have 2 to the power of n minus 1 times A, or just that's equal to 2 to the power of n minus 1, and here we have 1, 1, 1, 1. All right. In a similar way, you can just do this B. We have space here. Okay, good. All right. All right. Immediately, I can just add one slide here. How about B? For B, let's use green. That is all about A. Now, how about B? Our matrix B is equal to 0, 1, negative 1, 0. So from here, how about B squared? That is 0, negative 1, 1, 0 times 0, negative 1, 1, 0 equals. So it is 2 by 2 matrices. So here we'll have 2 by 2 matrix. 0 times 0, 0, negative 1 times 1, that is negative 1. And here, 0 times negative 1, 0 minus 1 times 0, that's equal to 0. How about here, 1 times 0, 0, 0 times 1, it is 0. And 1 times negative 1, negative 1, 0 times 0, so here we have negative 1. Or I can just write it as negative 1 times, here we have 1, 0, 0, 1. Which is equal to, actually, you must be familiar with this matrix. That's just an identity matrix. So that's equal to negative 1 times I. So now, if I write here B cubed, what is B cubed? B squared times B. And B squared, we have just computed here. That is negative 1 times I. And here we have matrix B. And as you know, see, this I is an identity element. If you just multiply this by any matrix, the result is that matrix. So that's equal to negative 1 times B. And how about B to the power of 4? That is B to the power of 3 and times B. B cubed, we have just calculated here. That is negative 1 times B. And here we have B. And so here we have negative 1 B squared, which is equal to negative 1 times, what is B squared? B squared equals this. That is negative 1, and here we have I. So here I can just write it as negative 1 squared times, and here we have I. Guys, here this one is scalar, right? Here we just have C, and this I is matrix, all right? If we have something like this, I times A, here is multiplied by matrix, so I can just write this matrix. But if you have a number, you cannot just disregard this I. Also, you need to write this, because otherwise, here we will have scalar only. This is a matrix, right? On the left-hand side, also we have a matrix. So what we notice here, one of this B squared, you have negative 1, B cubed, also negative 1, right? B4, and here we have plus, right? So again, if you just continue here, let's do this one more time. B to the power of 5, that's equal to b to the power of 4, and here we have b. B to the power of 4 is this, so that is negative 1 squared times I, and here we have b, right? Which is equal to, okay, to the power of 4. Okay, this negative 1 to the power of 2. Here we have b. Okay, that's equal to negative 1 squared, and here we have b, which is equal to b, right? So the first one, here we have just this thing, the result. One of this 3, and here we have just minus b, right? Minus 1 times b. And raised to the power of 4, it is just I, right? I. And raised to the power of 5, again, it is b. So what we have here is something like this. When it actually n equals, let me just write here. If you just make a table here, okay. And this one is n. Here we have b to the power n. All right. You're just trying to find a pattern here. When n equals 1, okay, 2, 3, 4, 5, 6, 7. Let me just add one more. It's 8. So when is b is equal to b, right? When it is 2 here, that's equal to minus I. Okay, just a minute. Hello. Hello. All right, sorry. Emergency call. Okay, gentlemen, here we have b, right? Here we have minus I, and when is b equals 3, here we have minus b, and when it is 4, and that's equal to just 1, here we have I. And when 5 is equal to b, and it repeats itself, right? b minus I minus b, and here we have, when it is 8, again it is I, okay? So that means that if here we have b minus I minus b, I. b minus I minus b, I. b minus b, I minus b minus I, right? So if, for example, let's say, that means that here, if we have b to the power, for example, 21, right? So when it is divisible by 4, as you see here, by 4, it is I. By 4, it is I. I can just write it as b to the power 20 times b, and b to the power 20, this 20 is divisible by 4, that's equal to I, that's I times b, and that's equal to b. So in this way, we can compute a given matrix given depending on the problem. All right, let's continue. Now we will talk about another concept, that is transpose of a matrix. Okay, and in transpose, usually we just use like apostrophe, and in some programming language, in Excel program, for example, you just write transpose and write the matrix inside the brackets, and it will just the Excel transposes the given matrix. And what do we mean by transpose? Okay, the transpose of an m by n matrix A is the n by m. As see here, just columns, like rows is changing into columns, and columns is changing to rows. Is the n by m matrix A to the power t, obtained by interchanging, or just interchanging the rows and columns of A. So that is the ith column of A transpose is the ith row of A for all I A. For example, let's say we mean that Here we have A, let's say whose entries are A, B, C, D. And here the rows of A are A, B, and C, D, right? Then how about A transpose? So that means that now this rows becomes columns. So here we have A, B, and here we have C, D. So here it is C, D, right? So this is how we transpose a matrix. Some examples. Okay, the transpose is sometimes used to give an alternative definition of the dot product of two vectors in terms of matrix multiplication. That is usually be used in proving some theorems. Okay, see here, if you just the dot product of u and v, what is it? It's just u transpose and v. That means that here, actually these are vectors, and also at the same time we can consider them as matrices, right? And u and v is just u transpose times v. And here it says the definition of two vectors in terms of matrix multiplication. Here we have u. Okay, let's say just one example. Here we have 1, 2, 3. And let's say v, here we have, let's say 0, 5, 7, for example. Okay. Now, what is u dot v? We know that we have to multiply the corresponding entries and add them up. That is 1 times 0 plus 2 times 5 plus 3 times 7, right? And at the same time, as you see here, it looks like a matrix multiplication. I can just write it like this, right? Here, if I just write like this, 1, 2, 3, and here we have 0, 5, 7, right? Actually, how can I do this one? Actually, what is this 1, 2, 3? That is just u transpose, right? Now here, I'm not putting dot here because on the right hand, on the left hand side, we have dot product. On the right hand side, we have matrix multiplication. All right. So we are just actually changing dot product into matrix multiplication. And because actually interchangeably we are going to use this, sometimes representing this product in this way, it is more practical or much better. Sometimes writing in this way, it is more practical or much better. You will see them soon in proving the theorems. So that means that here we have, okay, u transpose, and this vector is just v. So we have changed dot product into matrix product. Okay. And also here we have A transpose, right? Here we have IJ that is just equal to AJI. Because this one is AIJ means, right? For example, here this C. What is C? Its entries A 2, 1, right? And how about this one? C here is index actually order here is 1, 2, because now here in the first row, second column, but here in the second row, first column, right? So that means that the transpose ij that just gives us the ji entry of this matrix. Okay, transpose the following matrices. For example, here, this one is, what is this? As you see here, this one is 2 by 3 matrix. If we transpose this, here we will have, what is it, 3 by 2 matrix, which is this. Now you see here, columns, right? It becomes here rows, 2, 0, 3, 1, and 1, 7, by the definition. The second one, how about this one? See here, this one is 3 by 2 matrix. If we transpose this, here we will get 2 by 3 matrix. So the first column, it becomes the first row of the first new matrix, and the second column of this matrix becomes the row of the new matrix. So that is the transpose of B. Here we have 9, 0 row. The first row, the first column is 9, 0. The second row is 1, 4. The second column is 1, 4. Third row is 2, 3. And here third row is 2, 3. And how about this one? As see here, this one is 3 by 1 matrix. If you transpose this, here we will have 1 by 3 matrix, right? So that is C transpose. Okay. And that is the last part of this section, I think, yes. And after that, you'll have break. Symmetric matrix, one of the very useful matrices. So a square matrix A is symmetric if A transpose equals A. That is, if A is equal to its own transpose. That is the definition of symmetric matrix. So as say here, even if you just transpose, nothing changes here. That is called square matrix, symmetric matrix. Why? As say here, along the diagonal, for example, here, right? When you draw the line, as see here, these twos are symmetric. These 5, 5 are symmetric. 4, 4 are symmetric. That's why it's called symmetric matrix. And here we only use the 4 square matrices. And so A transpose, if you transpose this, you just, how does it reflecting along this diagonal, right? Nothing is changing. Still, we obtain the same matrix here. That's why it is symmetric. So how about this one? If you drew a line here along the diagonal, you see here, these entries are symmetric, right? So that's why actually it's called symmetric. Even if you just transpose this, transposing means drawing a line, we're just flipping over this line and we get the same thing. That's why it's also symmetric matrix. There's only one way to happiness, and that is to cease worrying about things which are beyond the power of our will. That's today's quote that I liked from, of course, from the Google. There's only one way to happiness. That means that if you want to be happy, that is to cease worrying about things which are beyond the power of our will. If you cannot change something and that is making you upset or sad, just cease worrying means finish worrying, stop worrying about the things and focus on good things. In this way, we can make our life much happier and enjoy our life more, everything. Guys, let's have some break. Okay, 10 minutes break. After 10 minutes, we will continue. Okay, see you after 10 minutes.